and decay. And we're not going to do very much with this, but this is something, if there's anything, honestly, in Algebra 2 that I'd like you to have just a glimpse of, it's this. Because this is something that is very applied, more so than the other stuff. Okay, what this has to do with, and the kinds of issues that this would deal with, would be things like if you wanted to figure out if the population of a town was growing at a certain percentage rate, you want to be able to project what the population is going to be in 50 years. That would be exponential growth. If you put money in an account that earns a certain interest, and you want to know how much money you're going to have when you retire from that account, yeah, that's what you would do. If you want to know if a substance is decaying, let's say you have a radioactive substance that's decaying, after 20,000 years, how much will be left? This is what you do. Okay? So let's take a quick look at this stuff. So exponential growth and decay. Now, the general equation we use is this. I'll use the way the book does it. It's going to be A times B to the X. Okay. Now A is what we call, this first number is what we call the initial value. Okay, so that's how much is there to begin with. Okay. The number that's being taken to the power of x is what we call the growth or decay factor. And x is the variable, but usually what it is it's a time. It's a time measured in, almost always, a time, and it could be in years or in weeks.
Minutes.
Or in hours or in minutes, or depends on the situation. It could be anything. Now, if you're talking about bacteria growing, maybe you're talking about minutes or hours. If you're talking about radioactive decay, maybe you're talking about thousands of years. Right? So it could be lots of different things. Okay, so in this problem up here then, what is the growth or decay factor? 2.42. That's it. It's 2.42. It's the number that's being taken to the power of x. Okay, now what that means. Now let's look at that for a second and see what that means. By the way, just to kind of put this in some context, when you talk in everyday language and someone says, man, that thing's just taking off exponentially or it's growing exponentially, what do they really probably mean?
Like it's
Yeah, it's just shooting off. It's growing very rapidly, right? And that's in our, we're familiar with that idea. If you were to graph an exponential function, here's what you would see. Okay, this is what it would look like. If I were to graph the function y equals 1 times 2 to the x, this is what it looks like if I connect the dots. Notice how it takes off and it starts to grow more and more rapidly, right? What's the starting value? 1. Okay? Now look what this is doing. Every time x increases by 1, we're going to multiply by 2 to a bigger power of x, right? So what if x is 1? Then that's 2 times 1, right? So it's going to double. If x is 2, we're multiplying our initial value, which was 1, times 2 squared, so multiplying by 4, right? If x is 3, we're multiplying by 8. Every time x increases, we just multiply by an additional power of 2, right? So do you see that what that's really accomplishing is this growth factor, in this case, is telling us by what factor is the amount increasing every time x steps up by 1. So it's doubling, right? If this number were a 10, then it would be increasing by a factor of 10. It'd be getting 10 times bigger every time x moved over 1, right? And of course, when you start to double things and then double again, those numbers start to get big pretty fast. 1 doubles to 2, 2 doubles to 4, 4 doubles to 8. Pretty soon you start to get some pretty big numbers. 8 goes to 16, 32, 64, 128, 256, 512. I mean, they start to get big in a hurry, right? So anyway, so that's what this curve looks like. When we say exponential growth, that's what you see. Now, exponential decay, on the other hand, would look like this. Exponential decay is going to do that. It's going to start to lose value very quickly initially, and then it sort of tails off. Okay.
So it's the same thing for increasing as it is for decreasing.
It's the same basic shape. Now, but what's going to make the difference? If this number up here, if the growth factor is 2.42, then that means that every time x increases, we're going to multiply the amount we had by 2.42, right? So that's growth, right? Everybody agree that's growth? Things are getting bigger in a hurry.
So if it was a negative, then
Well, hold that thought.
sorry.
Hold that thought. You're on the right. I mean, I know it's good thinking, but I want you to just hold that thought. You'll be able to answer your own question in just a second. So that's growth, and the growth factor is 2.42. Okay, what about this one? Whoops, hang on. I don't want to do that one. I want to do a different one. I want to do maybe, hang on. I want to do, no, I want to do that one. Okay, this guy, right here. Okay, take a look, please. We're getting sidetracked. Can't afford it. Can't afford it. We don't have time. What's the growth or decay factor there? 0.89. Okay, now think about that. If that's the growth or decay factor, is 0.89, then every time x increases, we're going to multiply the amount that we had by 0.89. Is that going to make it bigger or smaller? Smaller. So is that decay or growth? Decay. So what distinguishes growth from decay then? Smaller than, okay, smaller than what?
Decrease from the original.
1. Yeah. Now think about that. If the growth factor were 1, would it ever change?
No.
No. Every time x increased, we just multiply the previous amount times 1 and keep it the same, right? So 1 wouldn't make any sense for us. But if it's a number bigger than 1, if the growth or decay factor is bigger than 1, then it's going to be increasing in its growth. If it's less than 1, between 0 and 1, it's going to be decay, right? All right? So that's decay. Now, a better way to do this, honestly, growth factors are great, but we're not used to talking about growth factors. What we're used to talking about is percent growth. That's something you might hear about a lot. If you read the paper, you're going to read that the economy is now growing at a, 2% rate of growth. What does that mean? A town in, let's say Sherwood, Oregon is growing really rapidly. Right now, it's got 12% annual growth. Is that a lot or a little? How do you know? Right, but that's the kind of thing you're going to see. You invest money in a long-term, let's say you invest in a mutual fund, and it guarantees a rate of growth of at least 7%. What the heck does that mean? Okay, here's what it means. Let's take one like this now. For the above function, first of all, what's the initial value? I guess we got to go through those. What's the initial value there?
1,647.
Yeah, right? The initial value is just the number that's out in front that's being multiplied by the base to the power, right? Okay, that's the initial value.
Wait,
Good.
so when you do this, 1,647 says 1.10 and then get the answer, then power it?
No. You have to follow order of operations. So you're going to do exponents first. So you take 1.1 to the 5, let's say, and then multiply that times 1647. Okay? All right. So that answer is that. Okay? Now here's the one I want to get to. Pay attention or you're going to miss this. Oh, what's the initial value there? How about that? 469. Yeah. This is the one that I want. Now I got to change it. Okay, what's the percent growth? Now here's how we do percent growth. For percent growth, what we have to do is we have to rewrite the growth factor in this way. For percent change we have to rewrite that as a times 1 plus or minus r to the x, where r is the growth rate, as we're going to write it as a percentage, but that's as a decimal. There's the growth rate as a decimal. Growth or decay. As a decimal. So in this case right here, if we have y equals 4284 times 2 point times 2.21 to the x, what's the initial value, A? 4,284. But how would we find the rate of growth, R? Well, that means that what used to be B, I have to write this way, right? So we're going to set B equal to 1 plus R. And if R is positive, it's growth. If R is negative, it's decay, right? So in this case, B is 2.21. So we end up with the equation 2.21 equals 1 plus R. Well, how do we solve that for R? No. Subtract 1. So we get R equals 1.21. Now that's the growth rate as a decimal. If I want to turn that into a percent, what do I have to do? Multiply by 100, which moves the decimal 2 to the right. So then R equals 121% growth. That's big growth, right? Now, but that makes sense, doesn't it? Because now think about this. If every time x increases, we're going to multiply our previous amount by 2.21, that's going to more than double it. Doubling it would be 100% growth, wouldn't it? Because what that's saying is what we had before, we're going to take all of that and add it to what we already had to get double the amount, right? So this is more than doubling. That's more than 100% growth. Now, what you're more likely to see is maybe something like this. If we're talking about growth of, let's say we're talking about the growth of, money in an account or something, then we'd have something like y is the amount of money. Let's say we put in $1,000 times 1.08 to the t. Now see if you can tell me here, what is going to be the percent growth there? It's 8%. It's 8% because 1.08
just even, and then 8.
Equals 1 plus R. So what's R?
R is
0.08. Good. Okay, so R equals 0.08. If we write that as a percent, we'll scoot the decimal over 2 places, so it's 8%. It's positive, so it's growth. Right? Okay. That's how it works. Okay, now what about this guy then? How about this one? Okay, I want to know what's the percent growth or decay here.
-9.
It's -9. Exactly, because if we take the growth rate, or the decay rate in this case, of 0.91, and we set that equal to 1 plus R, right? And we solve for R. If I subtract 1 from both sides, don't I just get R equals -0.9? 0.91 minus 1, written as a percent. R equals -9%. So we're losing 9. If you have a car, as soon as you drive a car off a lot, it's going to start depreciating like this. Every year it's going to depreciate by a certain amount. It loses a certain percentage of its value, unfortunately. So you don't want to spend a lot of money on a car. Spending money on a house is a good idea because they appreciate.
Not all the time.
What's that?
Not all the time.
Cars?
The houses.
Oh, well, true. But usually in Pendleton, you're pretty safe.
Yeah, depends on how you treat it.
Yeah, don't let Chad start your car.
Okay.
He'll
Point,
go
point taken.
crash into shrubs.
Okay.
A couple curves.
All right.
Those shrubs are still destroyed. Because they have not started growing back yet.
Okay, I'm going to show you one other little trick with this. This is kind of nice to know, and this isn't really on the assignment. But if you want to know, whenever you're talking about growth rate, a good thing to do is calculate the doubling time. There's this cool little rule called the rule of 72. All you have to do is, the rule of 72 says this. The rule of 72 says that 72 divided by the growth rate as a percent equals doubling time. So now that really puts things in perspective. So if we say that Sherwood is growing the population is growing at a 12% rate, that may not sound that bad. 12%, 12% is just, that's not even close to 100%, right? That's not that big a deal. It doesn't seem like it. But if you calculate what that would really look like in real terms, and think about it in terms of your life, 72 divided by 12 is 6, right? So the doubling time is 6 years. Now imagine that for a second, 6 years. So in the time that you went from first grade to graduating from high school, Sherwood would go from a population of, say, 40,000 to 80,000 to, that's 12 years, right? So 2 doublings. So from 40,000 to 80,000 to 160,000? Are you kidding me? You can't add that many people to a town that quickly and have schools built and have the roads paved. I mean, it couldn't happen, right? I mean, it just would be disastrous. And so what you always want to do when you think about, when you hear a percentage, always translate it into a doubling time. That's the way you can really kind of get a feel for what does that number really mean. So just divide the 72 by the percentage. And so when we talk about the U.S. economy, I mean, here's another ridiculous thing. People have this expectation, I'll get on my soapbox for a second. People have this expectation that our economy should always grow at a rate of over 4%. That's ridiculous. How can the economy, if it grows at 4%, it's doubling every 18 years? You get double the size of the U.S. economy every 18 years? I don't think that's going to happen, though. That's not sustainable. I mean, it's, you can go through periods where it's going to grow like that, but then look what happens. If we go through a period, then it's always going to slump a little bit. It can never sustain that kind of growth. It's impossible. If you look at, how about this one? If you look at world population growth, you look at world population growth. If right now the world is growing at a rate of, what is it? I just saw this. I can't remember what it is right now, but there was it slowed down a little bit.
Yeah.
There was a period where the world was growing, the rate of growth of population was really pretty high. I mean, it was something like 8% or 9%. And so that would be doubling the population. I mean, you could never possibly sustain that. The planet couldn't hold on.
If you get too heavy, it swallows the atmosphere.
That's why
people
people
die there.
Well, I mean, it's,
Die fast enough. I know that sounds bad.
Exactly like